Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to start talking about triple integrals, which actually are going to play a pretty big role in really the remainder of the year now at this point. A lot of the last chapter of the year involves these things. So the idea of them is honestly just, you can kind of extend it perfectly from double integrals. So if you remember, a double integral, right, is a double Riemann sum, and the idea was like you're summing over, basically there's like a thing in the xy plane that's just like some sort of grid, and so we're summing over in one direction in all the x's and then all the y's, right, and we're doing like a Riemann sum, and then now, like what we're going to do is we're going to like let it also extend up into z, right? And we're going to create a 3D, object that we're summing over, which is kind of weird. But basically we're going to be imagining little cubes, like as we allow L, M, and N to get larger and go to infinity, we're basically going to create more and more and more of these cubes, so they get smaller and smaller and smaller and smaller. And then really like what you can think of is basically when we calculate a triple integral over a rectangular prism, so this, object is what we're calculating the integral over, the triple integral, we really are finding like four-dimensional hypervolume. And I have a joke of high school. And, there's a lot to be said here, and I won't get into it too much. You can truly actually conceptualize four-dimensional hypervolume. I worked in something called higher dimensional topology, and I worked pretty much exclusively in 4 dimensions or even higher. There's very good evidence that the world is at least 4 dimensions, like literally spatial dimensions. There's a lot to talk about there, and I don't need to get into it too much. So there is some reason why we would maybe want to know this. But another thing to just kind of keep in mind is that they don't necessarily have to be always about like area, volume, distance, these kind of things. Like integrals don't have to be understood that way. You absolutely could just think of calculating some sort of physical property. And actually that's what kind of Chapter 16 is going to get into, and you'll see a little more about that there. But like integrals can be used to calculate like mass, electric charge, the center of an object, like the balancing point sort of. They're used actually in probability a ton. So there's something in probability called like a joint density function, and I'll just kind of really quickly write it here. So it's given typically with capital letters for x and y. So these are basically, this would be understood as a probability of x and y here basically occurring in the region like D or whatever you are integrating over. But you can also extend that probability like function to x, y, and z. And now you're thinking about what's the chance that like x, y, and z occur in some, rectangular kind of 3D area, basically. So they're not always area volume stuff. But a lot of times that's like an easy way to teach them to people, so we start there. In physics, basically, you'll learn about other physical meanings of integrals, and not for a while, because those, honestly, to get to triple integrals in physics takes a little while. But for right now, I just want to talk about how to compute them, because that is basically what we need to cover in math. So to start off, I just want to do a sort of a straightforward one. So this is my function of 3 inputs, and I want to integrate over b, and b is a nice like box. It's got like closed bounds for x, y, and z. And this is basically the box down here. So, if I take like you have -2, 0, 1, as like a lower bound in the bottom corner over there, right? You can see how these points correspond to those, right? But this is what we're integrating over. So before we were doing 2D objects, you know, and integrating over those. Now we're integrating over 3D objects. So I am literally going to find the amount of hypervolume below this, above this thing, okay? And if you look at this, I would personally do I would probably do it doesn't really matter too much, but maybe do either the y or z integral first, because the powers are smaller. So that's kind of how I'm thinking of it. So let's do first let's just set everything up. So x squared y z. We'll do z y x. We'll kind of just go backwards like that. So z is running 1 to 5. Y is running 0 to 3. And x is running -2 to 1. And then it's all polynomial stuff. This is a polynomial in 3 variables, which is nice. So z is just, you know, if you integrate that, this stuff's constant. You do z squared over 2. So you're going to have x squared y z squared over 2 going 1 to 5. Get the rest of this stuff here. And then if you simplify that, you're going to get this. And then you do your dy integral, and you just get y squared over 2, which the 12 and the 2 are going to be nice. So that would simplify to this. And then lastly, we got to go plug that in, I guess. So that would be -2, 1. I think that's 54, because this was a 3. 54x squared dx, right? And then the last one, right, x cubed over 3. And if you do that one out, running out of room very quickly, you're going to have 18x cubed -2 to 1. And then that would be, 18 plus 144, which is 162. So, it should look very familiar to like how we've done double integrals over a rectangular kind of region, right? Same kind of thing. Think about maybe what you think is easiest to do first, because you can kind of flip around these orders any way you want. That's kind of our easiest case. Next case is general regions, right? So, before when I taught double integrals, we did a whole day on this. And then we talked about general integral regions for a while and defined the terms type 1, type 2 and stuff. So here, there's a few more things to consider. You can have so in terms of like how many orders of integration there are, let's just start there. You have 3 choices in the beginning, and then there's 2 more after that, and then there's 1 more after that. So there's 6 options for how to integrate, right? Like you could do dx, dy, dz, dy, dx, dz. That's going to be a different order, right? Those kind of things. So there is a specific naming system for these different orders of integration. And it's kind of a tiered system, basically. So I'm going to go through these pictures now, kind of. So since there's now 3 options for where to start, it makes sense that we can go up to type 3, right? And so what you see in this picture is one where you're integrating vertically in the z direction first. So if something starts off as dz, then that is actually what we call a type 1. If it starts off, so here you're integrating, like this could be an infinite kind of cylinder sort of looking thing, and you're integrating along x first, then that is type 2. So if it starts off dx, that's type 2. It's right there, actually. And then lastly, if it's one that you can kind of project onto the the XZ plane, and so it's kind of infinite along the y direction, that is a type 3, and that's one where you would start off with a dy integral. So vertical, like you can think about it in terms of projections too. If you project onto the xy plane, that's kind of the plane we're most used to, which is why I think it gets dz, or type 1, I mean. And then yz, I don't know. It's just arbitrary, but I guess there's no nice pattern for these two. But YZ plane, if the projection lives over there, it's type 2. And if the projection lives in XZ, it's type 3. The weird thing is that that's sort of just like what I like to call tier 1. And then there's like tier 2. So both of these are type 1. These are different like kind of objects, right? So their tier 1 is, I guess I should write the word tier. Tier 1, they're both considered type 1 integrals, because you're going to be doing like one where you project down into the xy plane. But you can see that like if you project certain things down, right, you could get this object versus this object, and this one you would want to integrate from here, trying to draw a nice small arrow, to here first, right? So that's like basically this one would be a z x y, and then this one would be, you'd go the other way, right? You'd go from that to that first before you go in x. So this one would be z y x. And so there is technically some naming systems out there where you'll see like this is a type 1 followed by a type 2, and so you'll see sometimes some books do this integral as a type 1/2. All right, and then this one is basically like a type 1/1 because its projection is also type 1. It goes dy dx in the projection part. So, long story short, by far the most challenging part of these things is setting them up, because you have a lot more all of a sudden, like it just hurts your brain to think about all the different directions to kind of consider. Especially when the problems are just like not given to you and you have to do the part where you have to think about what is the best order here, and trying to draw these kind of things like E is much harder than trying to draw things like D, which we did for double integrals. So we will spend some time with this, definitely. It's tough. All right. So the first one I just want to do, I want to evaluate triple integral of f of xyz equals z over the region E. And E is the solid formed by the tetrahedron that's bounded by the 4 planes, x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. And then, so let's try and draw what that would look like. So in 3D, I'm going to try to draw what E looks like. So x equals 0, y equals 0, and z equals 0, right? That's just going to basically keep me in the first octant here. So like the one that's kind of closest out of the page. And then x plus y plus z, the easiest way to visualize that, let's do it like yellow or something. If you plot the intercepts, right? So we have an intercept here at 1, another one at 1, another one at 1. Basically, it's a plane that goes through those points, right? And so if it's bounded by the axes and that plane, you're basically having your tetrahedron is like this inner kind of triangular thing in there, right? So visualize that as 3D, not as 2D. And honestly, it might have been better to even do it that way. So it's the tetrahedron that's just, its wireframe is given by this right here. And that kind of region, in terms of what kind of type it is, whether it's a 1 by 1, 1, 2, 2, whatever, 1, 2, it's really any. It's basically the nicest kind of region, because you can think of it as integrating, in Z, like down to this triangle here, and then you can do the integral down there, the double integral, or you can think of going over to the XZ plane, or you can think going over to the YZ plane. So just to maybe show you it doesn't matter, let's just do something different than just Z, Y, X. Let's do X, Y, Z. So if I do X, Y, Z, that would be like a type 2/1 region. Not that this stuff matters that much, but I'm basically doing type 2 followed by a type 1. All right, so now we have to get the bounds of all of this, and you basically, it's not too bad, because you have, Z equals 0 is one of the, all of them, Z equals 0, X equals 0, Y equals 0, all the lower bounds are going to be 0, right? It's probably not too hard to see that. So all of these, honestly, I can go 0, 0, 0. The upper bounds are what's a little different. So I have to get X equals something here for 3D. And so I just take this equation, right? And I just solve this one for X, which would be 1 minus Z minus Y, right? That would be the upper bound if I'm projecting it into the YZ plane. And then the YZ plane, if I draw that thing out, right, it's going to just be a diagonal line, 1, 1. And then if you projected this plane into YZ, the only thing that's left over are Y and Z. You have no more X, right? So this line is Y plus Z equals 1, or I'm going to need it with Y equals, so this is Y equals 1 minus Z. That would be the plane in the YZ plane, right? So I'm now doing, this is my region like D, let's say. Yeah, so then I get 1 minus Z right here. And then the last one is nice because everything has an upper bound of 1 in one dimension, right? 0 to 1, 0 to 1, 0 to 1. That's probably the hardest part. Then it's just setting this, or solving this thing out, which isn't as bad. So I'm going to kind of fly through this part. So the first integral, you're just going to get another X, plug this in. Then you would get, let's see, 0, 1, 0, 1 minus Z, Z times 1 minus Y minus Z, dy dz, which really is just polynomial. I think I'm going to actually be even more lazy. So I'm going to just do Z minus Y minus Z squared, and then dy dz. It's really quite a nice problem at this point. You'll get Y squared over 2 there. You plug this in. I'm going to let you finish this thing off. I'll tell you the right answer is 1 over 24. But really, at this point, that shouldn't be too bad, that double integral. All right, so one more here I just want to do. So I want to evaluate this thing. And E is the region bounded by the paraboloid right here, x squared plus z squared equals y, and the plane y equals 4. So basically it's cutting off, y equals 4 is just going to be a plane right here, and this plane just cuts off the paraboloid, and so you get this point 4 is right there, and you just get that kind of bowl looking thing. So this is one that I like because it kind of shows you how you can mix and match units. So the way I think about this one, I would actually want to crush this thing back into this plane. Okay, so basically I want to do a dy integral first. Then what's going to be happening, right, is in the xz plane, you're going to have a circle, right? And it's a circle that basically, since it's a circle, you would want to use polar. So I would do a rectangular kind of integral here for the first one, and then I'm going to follow it up with a polar double integral, which you can absolutely do. You can do that, which is kind of cool. Okay. So I might even do this. This is okay to do. So since I know I'm going to change some coordinate systems, I'm going to just I'm going to call that region R for right now, and I'm just going to like integrate over R in a little bit. So I'm not even going to worry about that integral. I am going to fill in something for the innermost integral. So this is my function, and dy dx dz. Another reason too I'm doing dy, right, is because this integral is really easy with dy. All right, so in terms of y, my my lower bound for this function is like the smallest y values, sort of, which are the paraboloid, right? Like this function right here, x squared plus y plus z squared, the shell of this paraboloid, right? That acts as the lowest bound, and then I go out to this thing right here, right? So that's like the plane that caps the thing off, which is right at 4. So 4 is actually an upper bound, right? And then the lower bound is like the blue paraboloid, actually, x squared plus z squared. So the first integral is nice. You're just going to do literally tack on a y, and then you're going to do 4 minus x squared minus z squared times by this thing, right? And then dA, let's just save right now. And now it's like a nice polar problem. So in xz world, right, we have that x squared plus z squared is r squared. Here we're going to do x is r cos still, r cos theta, but now z is r sine theta. So this is my kind of important conversion, which is a little different than, you're used to doing it in xy, but you can absolutely do that in xz. And then, in terms of how big this circle is, that would just come from the intersection of the original equation with the y equals 4, right? So we have like 4 equals x squared plus z squared is actually this circle right here. And so its radius is 2. So now I can actually go back to my double integral and plug in everything. So we got a full circle, 0 to 2 pi. We've got a radius of 0 out to 2, right? And that's going to be doing this whole circle in there. And then we got a 4 minus r squared. And then we've got times by the square root of r squared, which is an r. But then we even have another one with the r dr d theta, right? So another one where no theta dependence, you can stick a 2 pi out in front. And so what you're basically integrating is that. I think I did all my math there, right. And very nice integrals. I'm going to just, again, be lazy. And I will tell you that you should get 128 pi over 15. So that is what you should get. So that is the hypervolume underneath this thing and over that thing right there. That's what we just did.